Good morning, afternoon, and evening, everyone, and welcome to HySky Mentally. Thank you all for joining us today from around the world. My name is Sayana Abraha, and I'll be hosting today's webinar on behalf of HySky Society. Before we begin, just a few quick housekeeping items. Today's session is being recorded. Please use the chat for the webinar to submit questions for our speaker. You'll be able to unmute at the end and ask your questions, and you'll have a time at the end for the audience Q&A. Please keep yourself muted during the presentation. I'm going to share the HySky's mission. So at HySky Society, our mission is to decarbonize aviation and aerospace through the use of hydrogen. HySky Society is a 501c3 charitable non-profit dedicated to accelerating hydrogen aviation through connection and community advocacy, awareness, education, and our core programs include HySky Connect, HySky EDU, Flying High, HySky Mentally, HySky Pod. And our vision is simple: clean skies for future generations through hydrogen-powered flight. We support the entire hydrogen aviation ecosystem, from hydrogen producers and fuel cell developers to aircraft innovators, researchers, regulators, and anyone passionate about sustainable aviation. And we do also have some announcements. On November 4th, HySky Society will host Flying High 2026, a global virtual aviation conference focused on the future of flight. The event brings together leaders across hydrogen aviation, aerospace, batteries, SAF, advanced air mobility, eVTOLs, drones, infrastructure, certification, manufacturing, policy, academia, and more. Confirmed speakers include leaders from organizations such as United Therapeutics, Zero Avia, Robinson Helicopter Company, Joby Aviation, GKN Aerospace, Parcel Group, Kawasaki Aircraft Corporation, Beyond Aero, GenH2, and many others. So Flying High is designed for anyone passionate about the future of sustainable flight, aviation, and aerospace professionals, engineers, researchers, students, hydrogen, fuel cell, battery, and SAF companies. Tickets are currently $75. And now we are excited to introduce today's distinguished speaker. Today's HySky guest is Dr. Barry Prince, Vice President of Hydrogen at FABRUM. Dr. Prince is a hydrogen technology leader with extensive experience advancing hydrogen innovation, having previously held leadership roles at the New Zealand Hydrogen Council and SIF Technologies. He earned his PhD in physical chemistry from the University of Canterbury, spanning analytical chemistry research and development, producing development, production planning, and strategic planning. Dr. Prince is passionate about accelerating the adoption of hydrogen technologies and advancing practical, scalable solutions for the future of clean energy and sustainable aviation. Today's presentation is titled Lightweight Composite Liquid Hydrogen Storage Tanks for Aviation. Please give a virtual applause to welcome Dr. Barry Prince. Barry, the stage is all yours.
Excellent. Thanks very much for that, Sion, and thanks very much for the invitation. We're keen followers of the HySky monthly sessions at FABRUM, so it's a real treat to have the opportunity to present to this group some of the work that we're doing in FABRUM in the hydrogen space, and in particular the work we're doing developing lightweight liquid hydrogen storage for mobility applications. So look, let's jump into it. I'm just going to start with a bit of an introduction to the sort of work that FABRUM does and a little bit about the company. So FABRUM is a New Zealand company. We're based here in Christchurch in New zealand. Christchurch is the biggest city in the South Island of New Zealand, with a staggering population of 500,000. But it is quite a innovative centre and a bit of a technology hub in New Zealand and this part of the world. FABRUM was founded by two graduates from the local university here in Christchurch, and one of the reasons they founded the company was to provide a pathway for local graduates, local engineering graduates in particular, to take their ideas and commercialise them and stay within New Zealand industry. New Zealand is a small country, population of about 5 million, and not mega industry here. And one of the challenges that we have faced over the years is what we call a brain drain. So young graduates often go offshore, go overseas to pursue their careers, chasing bigger dollar, bigger industry. So FABRUM had that in mind when the founders set up the company, and also had an intent to foster the creation of technology that would have a positive impact on the world. So the sort of ethos that we work within is the idea of doing more with less and treating softly and that sort of ethos. So at our heart, we're a precision engineering company with deep expertise in cryogenics. We manufacture solutions for superconductivity applications. We manufacture components for superconducting engines for aircraft applications. And we build small containerized liquefiers that can be deployed and operated at the site where they will be used. And we stepped into the hydrogen space about 6 or 7 years ago when it was clear that hydrogen a decarbonisation vector for the planet. Well, for that to be true, liquid hydrogen is a key part of that, right, of that whole hydrogen ecosystem. And so with all of the expertise in cryogenics, FABRUM, felt it could make a significant contribution in that space as we're currently doing. So just to give you a bit of an idea of the sort of work that we do in the hydrogen space and our expertise, I'm just going to show a recent project that FABRUM was involved in. So this is a bit of drone footage from a mine site in Western Australia. The client for this project is a company called Fortescue, big iron ore mining company based in Western Australia. Okay, and they wanted to demonstrate that they could decarbonise their mine site. Specifically, they wanted to demonstrate they could run their big haul trucks on liquid hydrogen. Okay. To do that, they needed a liquid hydrogen liquefier on site. So Western Australia is a fairly remote place. Perth is the capital city of that state of Australia. Perth is the most remote city in the world. And this mine site's about 1,000 kilometres north of Perth. So very remote location, very punishing environment. The temperatures regularly go above 50 degrees Celsius. And it's a very dusty environment. So what you're looking at in this photo, in the background under that canopy are electrolyzers. They're being fed from electricity from a solar array, so they're producing green hydrogen. That's fed down to a pipe through a pipeline to the plant at the front here. That's the hydrogen liquefier that was designed and manufactured by FABRUM. So all of the cryocoolers that are doing the cooling of the hydrogen are in the 3 containers in the foreground, and the containers just behind that have all the heat rejection and control systems. So this liquefier produces about 400 kilograms of liquid hydrogen in a 24-hour period. That liquid hydrogen is stored in the cryogenic storage tank you can see in the foreground. And then beside that big yellow boom you can see hanging underneath it is some hoses, the vacuum jacketed lines, and that's the refueling line. So that boom can swing around and refuel vehicles. And the primary vehicle that it is refueling is this. This is a liquid hydrogen mobile refueler. It carries about 600 kilograms of liquid hydrogen, and it has all of the infrastructure on board for doing liquid transfers. It's built into a standard 20-foot ISO frame, so it can be easily transported or relocated. And this vehicle will then refuel liquid hydrogen into a couple of other vehicles. Firstly, the vehicle on the right-hand side of this, it looks maybe a bit more like a building than a vehicle, but you can see it's on tracks there. It can travel around behind the excavator on the left. That excavator is 100% electric powered and difficult to see, but there's a big power cord running along the ground to the vehicle on the right. It's called an off-board power unit, and the off-board power unit has storage of about a half a ton of liquid hydrogen that is feeding fuel cells, producing about 1.3 megawatts of electricity to power that electric excavator. But ultimately, this project was about proving these these trucks could run on liquid hydrogen. Okay, so this is a 300 ton, the beer haul truck. This truck would typically consume about 2.5 to 3 tons of diesel in a 12-hour shift. This truck running on liquid hydrogen will do that 12-hour shift by consuming about 500 kilograms of liquid hydrogen. Okay, and that hydrogen stored in 2 of those FABRUM tanks, is one on each side of the vehicle. And so, as I say, this is quite a nice demonstration of the sort of work that FABRUM gets involved in. Everything in this project that had anything to do with liquid hydrogen was designed, manufactured, deployed by FABRUM. So that includes the hydrogen liquefier plant, all of the liquid storage, the liquid transfer systems, dispensing and refueling systems, onboard storage, and the storage delivery systems. So if you look at the products that FABRUM manufacture, they're largely underpinned by 2 technologies that the company has developed. So I'm just going to talk about them on this slide. So firstly, on the left, we have a proprietary cryocooler. So in the middle of that circle, you can see that cryocooler. It's essentially a very powerful refrigerator, works at the same principle as your domestic refrigerator at home, compressing and expanding a refrigerant gas, but much more powerful, right? And that underpins all of our products that deliver cooling power. So it's hydrogen and oxygen liquefiers, it's natural gas liquefiers and boil-off gas management systems, and of course our hydrogen liquefiers and boil-off gas systems. On the right-hand side of this slide is the other core bit of technology that FABRUM has developed, and this is manufacturing techniques that enable us to build these super lightweight storage vessels for liquid hydrogen. That, of course, is what we're going to get into in a bit more detail as we roll through this talk. So before we get onto the tanks, what are the other products around the cryocooler that FABRUM are producing? Because these do also have some relevance, as we'll see, in the aerospace sector for hydrogen powered flight. So firstly, the hydrogen liquefiers. We've talked about the larger one at the top left of this, the system that's installed in the Pilbara in Western Australia. To the right of that at the top is a system built into a 40-foot shipping container that will produce up to 75 kilograms of liquid hydrogen a day. That system pictured there is currently being installed in Germany at the Karlsruhe Institute of Technology at their energy lab. In fact, it's at the heart of their energy lab, producing liquid hydrogen that's underpinning all of the R&D that they're doing for cryogenic hydrogen at that site. Bottom right is a smaller, probably smaller scale liquefier that we produce. We call it a development scale, and it can be configured to produce from 3 to 20 kilograms per day. The liquefier pictured there is operating at in Kemble, Cotswold Airport in the UK, actually the site where Zero Avia are based, and that's been operating for a few years there, is producing liquid hydrogen that's supporting the development of technologies for liquid hydrogen in aerospace. And finally, on the bottom left is a system that's in a 20-foot container. It can operate as a liquefier and produce 30 kilograms a day. Liquefaction rate. Actually, this system uses a different technology to the other liquefiers on this page. And so as well as operating as a liquefier, this can operate as a reliquefier, okay? The difference being the temperature of the hydrogen that is being supplied to the unit. So a liquefier is taking hydrogen from ambient temperature down to the condensation point. A reliquefier is taking boil-off gas, so it's taking cold hydrogen that's in gaseous state and just dropping the temperature a smaller amount to recondense it, and so that's a boil-off gas management system. That system on the left is actually being deployed as a boil-off gas management system, and in that mode, it manages a much larger quantity of hydrogen, of course, because it's only cooling a smaller amount, so it can recondense or reliquefy a much larger quantity of hydrogen in a day than that 30 kilograms. The plant pictured there is currently being installed at at a site in the US in Washington State. Actually, it's a plug power site, and it's going to be managing the boil off associated with a liquid to high pressure gas refueling site. So there's two main sources of boil off gas in that space, and that's the normal evaporative rate of the liquid hydrogen storage tank, but also the cryogenic pumps that are used to compress hydrogen to boost the pressure for refueling, produce low pressure hydrogen gas that needs to be managed, and that's what that unit is doing. And I think we've got another picture of that system here that talks about boil-off gas management. So these systems, both the liquefiers and the boil-off gas management, have, as I say, some relevance to aerospace applications, in the sense that these can be deployed in the field, right? They can be deployed at the point where liquid hydrogen is being refueled or is being dispensed. And so having cooling power at those locations gives you a lot of options and more flexibility to build an efficient liquid hydrogen system. One of the big challenges we all know with managing and building liquid hydrogen systems is managing the boil-off gas and building an efficient system where you don't end up venting large quantities of hydrogen. So having the ability to deploy cooling power at the sites that the hydrogen's being dispensed or being used gives you some flexibility to support that. All right. So that's the cryocooler technologies. And then the other technology, of course, is the composite tanks, which is the purpose of the webinar today. So we're going to dig into this, and FABRUM builds a range of composite tanks for mobility applications that really care about lightweight tanks, right? So it's primarily in aerospace, but also for motorsport applications. There's a lot of interest for these tanks. So we manufacture conventional double skin cryogenic tanks where there's a liquid containing vessel that's a pressure vessel surrounded by a vacuum jacket for insulation. In addition to that, FABRUM has a patent for what we call a triple skin tank, and that overcomes a couple of the major challenges with a cryogenic fuel tank with regard to the efficiency with which the tank can be refilled, particularly from ambient temperatures. And I'm going to explain a little bit more about that triple skin tank in a minute. But before we dig into these tanks, I just want to step back a bit and just, talk a little bit about, why we care about this. Is there really a future actually for hydrogen and liquid hydrogen in aviation? And how important are these tanks for this? I don't want to belabor the point for this audience. I think we're all fairly well versed in these arguments, but it's maybe interesting just to look at the arguments through a slightly different lens. So let me just touch on this quickly. Firstly is the question about, is there really an economic argument that hydrogen flight, there is a place for hydrogen flight? And this is a slide that I've always found makes quite a compelling argument for this. This slide was put together by an Australian company that's developing hydrogen-powered flight, the Australis Aircraft. And the graph on the left, you can see the vertical axis is the cost per available seat kilometre, and they've mapped that out for hydrogen, a couple of their versions of hydrogen-powered aircraft compared with jet A fuel for a Dash 8, for example. And you can see, depending on the price of your liquid hydrogen, you can make an argument that you can run a lower cost operation than using fossil fuels, right? Depending on the price of the liquid hydrogen. But if liquid hydrogen can meet the price points that are being projected, certainly in the range of, say, 2030, then these arguments really stack up. The thing that I find quite very interesting on this plot, though, is that histogram. You can see that's the passenger traffic histogram. And what that shows is 50% of all CO2 emissions from air travel arise from flights under 2,200 kilometres. So right in the sweet spot where these hydrogen-powered flight technologies are going to be operated, right? So there is clearly a place for liquid hydrogen powered flight if these technologies can be brought to fruition. Why does it have to be liquid hydrogen as opposed to other forms of hydrogen? Well, that comes down to the question of specific energy. And again, this is a plot that is shown in different forms that makes that point. And so what this plots is the specific energy, the energy per kilogram of your fuel system versus the horizontal axis, which is the energy density, how much space your fuel system takes up. The critical metric for aviation, and not just aviation, all of the hard to abate sectors we're talking about, mining, aviation, heavy transport. Why are these sectors called hard to abate? It's because they rely on this characteristic of fossil fuels that it has a very good specific energy, right? And it's very difficult to find an alternative fuel for that. Batteries have come a long way, compared to old lead acid batteries. When you look at lithium ion batteries in terms of the specific energy and the volumetric energy density of those, they've improved orders of magnitude, but they're still a long, long way away from competing with fossil fuels. With respect to this metric, it's not to say there's no place for batteries, but with regards to this specific metric, they've a long way to go. So as you can see on this slide, liquid hydrogen, and in fact, liquid hydrogen is really the only zero carbon fuel that can outperform fossil fuels with regards to this metric, this specific energy. But it doesn't happen as a matter of course. What this plot shows is not just the specific energy of the fuel itself, but the entire fuel system, the storage and the fuel delivery system. Okay, so we all know that hydrogen has a much better specific energy than carbon-based fuels, but you still have to store it somehow. So you can see on this chart, for example, that gaseous hydrogen does not perform as well. And the reason for that is the weight of the storage tank needed to store hydrogen at those pressures really counts against you with specific energy. Okay. So the takeaway point is liquid hydrogen can outperform fossil fuels with regards to the specific energy, but only if you have sufficiently lightweight storage and delivery systems. All right. And so that's why composite tanks are of so much interest. What are the properties of the composite tanks that really attract, or the key ones are related to that weight, right? The two graphs on the left-hand side, the density of composites is much less than metal tanks, so it's lighter, but still has very good tensile strength, much better than metal tanks. And the thermal conductivity of composite is much, much lower than metal. So the thermal performance of a composite cryogenic tank will outperform a metal tank. But also the composites, with regards to the number of pressure cycles that they can undergo, far exceed what metal tanks by up to a couple of orders of magnitude over metal tanks for the number of pressure cycles. Now, it's not to say that there's no challenges with building cryogenic tanks, particularly for hydrogen. Composites, by their nature, are known to be quite porous, and hydrogen, of course, is the smallest molecule. So managing the permeation of hydrogen through these vessels is an important part of developing these tanks, and also understanding really the lifetime of these tanks, not just with regards to pressure cycles, but pressure temperature cycles. They'll be cycling temperature from ambient to minus 250 degrees, right? So there's a challenge there, but there is a growing body of knowledge around these challenges that's being developed not just by FABRUM, but by others around the world, and that growing body of knowledge is showing that these challenges can certainly be overcome. They're not showstoppers. Fair to say that I think there's an acceptance that cryogenic fuel tanks on vehicles will be composite. Composite will be the material for choice in these sort of applications in the future. Okay, so what does an ideal composite tank look like? Well, I'm going to talk through some of the considerations that go into that when we're designing these tanks. And as you'll see, an ideal tank depends on a number of factors. There's the system considerations, but also operational requirements play into it. And actually, as we've heard in other HySky talks, the best outcomes are achieved when you look at the tank holistically with the whole system. So rather than developing a system to a point and deciding what are the characteristics of the tank that you need to fit into that, you really want to look at the tank along with everything else from the get-go. But first, so let's look at some of the considerations for a composite fuel tank. I'm going to start with the operating pressure. And the key point here is the headline of this slide, that the real benefits of liquid hydrogen are achieved at low storage pressure. The basis for this is the relationship between the density of hydrogen and the applied pressure. The density at the saturation point, right? So hydrogen has this, I've always thought, a little bit counterintuitive property where it essentially swells up as the applied pressure increases, the density reduces. It's not actually unique to hydrogen. You can see on this chart, water and nitrogen and methane all have the same characteristic, but it's more marked for hydrogen, and it's pretty significant. If you're operating a liquid hydrogen tank at 3 bar gauge, you'll have a density of 63 grams per litre, thereabouts. If you're operating at 10 bar gauge, that drops a fairly staggering amount down to 47 grams per litre. So what does that mean? Firstly, it means that for a given volume of tank, you've got a lot less fuel on board, right? But not only that, because the tank with less fuel on board is also containing a higher pressure, so it needs to be heavier, right? So if we were going to build a composite tank with 40 kilogram capacity, if we were building that to operate at 3 bar gauge, it would weigh about 50 kilograms. And 10 bar gauge, you're looking at maybe 90 kilograms, that sort of range, right? So both of these things act together to the detriment of your gravimetric index of your system, the mass efficiency of the system. So you have like this double whammy effect. And so the gravimetric index for that system, our 40 kilogram capacity system operating at 3 bar G, would be somewhere near 45%, which is to say 45% of your fuel system is fueled, right? But at 10 bar gauge, that would drop to about 30%. So pretty significant. So if you can operate at lower pressures for your liquid hydrogen storage, you have some significant benefits in the gravimetric index of your fuel system. All right, so the second consideration I want to talk about is the dormancy. So dormancy relates to the amount of time if you fill a cryogenic fuel tank at low pressure, it can sit there for a period of time, building pressure until it will ultimately hit a relief pressure and start venting hydrogen. And that's the dormancy period, the time between filling to the time that you start venting hydrogen. And people care about dormancy because, you don't want to fill a liquid hydrogen powered aircraft and then have it sitting on the runway having to vent hydrogen. So it's an important consideration. The dormancy is related to the insulation of the tank, right? The smaller the heat leak, the longer the time for the hydrogen to boil off and build pressure to the relief pressure. But the point I want to make here is that there is a trade-off in building a good dormancy, because insulation typically adds weight. So you can build a tank with a lower heat leak and a longer dormancy, but it will likely be a heavier tank. So the point of this slide is to make that point. If you imagine a system, we're looking here again, a 40 kilogram composite tank, 40 kilogram capacity composite tank, and let's say it's on a system that's feeding 120 kilowatt fuel cell. If we were to design that tank, it could easily have a 10 watt heat leak, and that would give it a dormancy of 48 hours. But you only care about that until the point that the fuel cell is being fed by hydrogen. Okay, the amount of energy, the amount of heat that you need to put into the tank to deliver hydrogen to a 120 kilowatt fuel cell is orders of magnitude more than the heat leak. that the tank has. So you're going to be putting in 750 watts just to evaporate the hydrogen, and then another 8.5 kilowatts to bring it up to the temperature needed for the fuel cell, right? So the point here is, as soon as you're operating the aircraft, you don't care at all about the heat leak of the tank, right? So it's important to design the heat leak of the tank that matches the use case of the tank. Okay, as soon as you're operating, you don't care about the heat leak, but so you don't want to be carrying around extra weight in your tank that is giving you a dormancy period that's actually not being utilized. All right, so let's talk a little bit about refueling of these tanks. And for cryogenic tanks, it's particularly important. For cryogenic fuel tanks, it's particularly important when you're refueling from ambient temperatures, right? So a particular challenge when refueling a cryogenic tank from ambient temperatures is how you can do it efficiently, how you can fill it quickly and minimize the losses. So typically, you would take a fairly extended period to fill a cryogenic fuel tank to slowly cool the vessel that's going to contain the liquid hydrogen, so that you don't thermally shock the tank. In the same way that if you pour boiling water into a cold glass, you can crack it. You need to change the temperature of these tanks slowly, and particularly for a composite tank, although it applies to metal tanks as well, you can thermally shock those. So you need to cool it slowly, and also then in cooling it, you're losing a lot of your cryogenic fuel, evaporating it and cooling the tank down to the boiling point of that cryogenic fuel so it can start to condense. Okay, so this triple skin tank deals with this by adding a third skin. And if you look at the diagram on the left, the third skin is inside the pressure vessel of a conventional double skin tank. So the cryogenic fuel would normally reside in that pressure vessel, but in this triple skin tank, there's a liquid vessel inside that which is containing the cryogenic fuel. Now, this liquid vessel is not a pressure vessel. It contains liquid hydrogen inside, and on the outside is gaseous hydrogen, boil-off gas, at the same pressure. So it doesn't have to contain any pressure. It can be extremely light, extremely low thermal mass. And so what this allows is you can cool that liquid vessel very quickly, and you can fill the tank very quickly, while the rest of the thermal mass of the tank is still warm, right? But you can be operating with a full tank while the rest of the tank cools down. So that happens. So you essentially offset the cooling of the tank from the fueling of the tank. And we'll look at that on the next couple of slides. But there is another significant advantage of this triple skin tank, and that is in managing one of the important safety cases for cryogenic fuel tanks, particularly on aircraft. There's always a concern for a cryogenic fuel tank about the safety case if there's a loss of vacuum, right? So if you lose vacuum in your vacuum vessel, you have air rushing in, you are delivering a massive amount of heat to the liquid containing vessel, which will generate a lot of boil off, and worst case scenario, you can think of a massive loss of fuel. So the triple skin tank here mitigates that significantly, because if there is a loss of vacuum in that vacuum vessel, the heat that is flowing into the tank is not in direct contact with the liquid containing vessel. Okay, that heat load is buffered by the boil-off gas between the pressure vessel and the liquid vessel. And we've done tests on these tanks, dropping the vacuum when they're full of liquid hydrogen, and that effect is very impressively and massively mitigated. And in fact, the preliminary tests suggest that the heat load on that tank would not even exceed the heat load that you would deliberately be putting into the fuel tank to drive the hydrogen out to feed your fuel cell or your engine. So let's just have a bit of a closer look at how the refueling efficiency works. So just looking at it, firstly, a conventional double skin tank here, and if you look at the chart at the bottom, it just it just plots the temperature of the pressure vessel in a double skin tank as it's being refueled, right? So it starts at ambient temperature, 300 Kelvin, and it drops down. Let's say you're fueling over 30 minutes or so, or cooling the tank over 30 minutes. The temperature drops to the condensation point of hydrogen, and then it levels out at that point. And in the top chart where you can see the amount of hydrogen either lost or filled into the tank, you can see while the tank is while the tank is cooling, you've got losses. There's no condensation in the tank. So you're not filling the tank, you're just losing hydrogen as boil off. As soon as you hit the condensation point, then the boil off levels out and the tank will fill. So how does that look different for a triple skin tank? So the grey lines in the background are the double skin tank. And now, if you look at that bottom chart, there's two traces now because there's two vessels, the pressure vessel and the liquid vessel, right? Now, the liquid vessel cools very quickly, about 5 minutes to cool that. And then once you hit the condensation point again, the temperature levels out. But look at the top trace of the bottom graph is the pressure vessel. The temperature of the pressure vessel is also cooling as the liquid vessel is cooling because of the boil-off gas that's coming out. But as soon as you start condensing in the liquid vessel, there's very little boil-off gas then, right? So the temperature of the pressure vessel levels out also. Now, if you look at the top chart, you can see the same effect as for the double skin tank. The losses that you're getting are really only occurred during the cooling of the liquid vessel. So over that short first period, and then they level out, right? You start filling the tank after 5 minutes when you've cooled that liquid vessel. So overall, the refueling time is much, much faster, maybe 3 times faster on the triple skin tank compared to the double. And the losses of hydrogen and refueling are even more significantly better, more than 5 times reduction in losses. Okay, so finally, I'm just going to make the point that to gauge the suitability of a tank, the ideal design for a tank, you need to consider the overall system, and that extends even beyond the aircraft. The whole system, starting from the right, considers how the hydrogen is going to be consumed, whether it's a fuel cell, internal combustion engine, jet engine, the conditioning of the hydrogen, how it's stored. That's all of the aircraft systems. But even before that, the refueling, where the hydrogen is produced, and the impurities in the hydrogen, those sort of things can play a part in this, but particularly the hydrogen liquefaction. Is the hydrogen liquefied remotely and transported to the point that it's being refueled, or is it being liquefied at the site that it's being dispensed, right? If you're liquefying hydrogen at the site that it's being used, that gives you a lot more control over the state of the hydrogen that's going into the aircraft, whether it's subcooled, what the saturation point is, and so on. So that can be a key factor in the design of your onboard systems, right? And so important to consider these factors, and the area on here that FABRUM gets involved is that red dashed box there. So from the ground, from the hydrogen liquefaction systems with our small scale hydrogen liquefiers, but also all the refueling infrastructure to transfer liquid hydrogen into the tanks on board the vehicle, and so then the storage and the gasification and conditioning systems to get it to the right pressure, temperature, flow rate to feed the consumption device. That's where FABRUM operates. All right. So what is the maturity of these composite tanks? We've developed a range of these tanks, and they've been fairly rigorously tested at various locations by some of our customers and us around the world. The picture on the left is one of our triple skin tanks that's undergoing vacuum loss testing at our liquid hydrogen test facility here in Christchurch. In the middle is a conventional double skin tank that's being tested at the Cotswold Airport site in the UK. That test went through a whole battery. That tank went through a whole battery of tests to validate heat leak of the tank, vacuum integrity, and various performance characteristics of it as a cryogenic fuel tank. And so on the right-hand side is one of our customers. That's Aero Delft. They're a student-led group out of the Netherlands, out of TU Delft University. And they are developing a single-seater aircraft, converting a single-seater aircraft to run on liquid hydrogen, and they'll be using a FABRUM tank for the liquid hydrogen on that aircraft. They are putting that tank through a whole battery of tests with their various support partners and collaborators. The test you can see in that picture on the right is a centrifuge test to validate that the tank can stand up to 9G accelerations in the XYZ directions. So in terms of where the technology is at, the performance characteristics of these tanks as cryogenic fuel tanks is now very well understood, and we're working through the compliance needed to get them on board aircraft and get them flying. And there's a number of companies that are working in this space, just sharing a couple in this part of the world. Crux Aerospace is a New Zealand startup that are converting a New Zealand manufactured aircraft called, it's an NZ Aero aircraft, 750X. It actually has some characteristics that make it very well suited to convert to a hydrogen powered aircraft in terms of its payload and the cargo space, and so on. So they will be converting that aircraft to liquid hydrogen. On the left-hand side is AMSL Aero. They're an Australian company developing liquid hydrogen-powered eVTOL aircraft and utilising FABRUM's composite tanks and fuel delivery systems on that aircraft. All right, so the final thing I want to just talk about is another initiative that FABRUM is launching down here in this part of the world. So this picture here is a photo from a temporary liquid hydrogen test facility at Christchurch International Airport. And later this year, we're establishing a permanent liquid hydrogen test facility at that site. So this site will have a hydrogen liquefier that can produce from 50 to 100 kilograms of liquid hydrogen per day. The site will support the development programs of these composite tanks and other liquid hydrogen technologies that FABRUM is developing, but is also available for the use of other organisations that have a need to get access to those quantities of liquid hydrogen and facilities where they can conduct some testing. It's actually part of a wider initiative by a group of organisations in this part of New Zealand that are working to develop a hydrogen ecosystem. And so, for example, one part of this is the Civil Aviation Authority in New Zealand has established what they call a sandbox airspace. And so there's various locations where the airspace has less regulatory constraints. One of those locations is within a 30-minute drive of Christchurch, and so you can carry out aircraft testing at that site without going through all of the normal regulatory hurdles for CAA certification. Essentially, you can accelerate your aircraft development programs by carrying out flight testing in those regions. So a lot of companies are looking to come to Christchurch to take advantage of some of these facilities here, liquid hydrogen test facility, the expertise that FABRUM can support with, and these new airspace, sandbox airspaces to accelerate their development program. So it's an exciting development for this region. This site will be the only of its kind in the Southern Hemisphere. It will be the only international airport in the world, we believe, that will be producing liquid hydrogen on site. So if any of you are looking for an excuse to come down and visit us in New Zealand, maybe this is the excuse you need. So we'd love to see you down here. This last slide is a shot of our temporary test site. It's a little video that I'm not going to play. It runs for about 3 minutes. But the YouTube URL's there, so you can pull that up. It runs through some testing that was recently done at that site. We were factory acceptance testing a hydrogen liquefier and using the liquid hydrogen to test some refueling protocols on some composite tanks, and there were some reasonable milestones that were achieved in that testing. So I'll leave you to take a look at that at your convenience. And so, yeah, what are the takeaways? Let's wrap it up there. I guess hopefully to this audience, it's not too difficult an argument to say that there is a place for liquid hydrogen powered flight. Again, for me, the fact that 50% of current aviation emissions can be mitigated by hydrogen is quite compelling, but it requires lightweight composite or lightweight fuel systems to make that a reality, and that's why the composite tanks that we're developing are of such interest. And also the small scale hydrogen liquefiers can play an important role in making these overall systems as efficient as possible. And finally, the liquid hydrogen test facility that will be up and running here in Christchurch by the end of the year will play an important role in the acceleration of the development of these technologies to enable liquid hydrogen powered flight in both in New Zealand and around the world. So let me stop there. I'll hand back to you, Simon, and happy to take some questions if there is any.
Thank you so much, Barry. Yes, we have a few questions in the chat from Suman. One is the source of hydrogen liquefaction, and second, regarding to the boil off GM in the field. How is the boil off managed with the Forsk's mining truck or for an aviation system, and the percentage of the boil off?
Yeah, okay. All right, so let me, in terms of the source of hydrogen for the liquefaction, well, it could be it could be from multiple sources. The hydrogen supply is separate from the liquefaction. These hydrogen liquefiers are quite small scale, so they're actually quite nicely suited to a small scale electrolyzer. You could sit a small electrolyzer in front to feed those sort of quantities of hydrogen into the liquefier. But equally, you could bring in hydrogen, compressed hydrogen, and feed it from that source. So the liquefier is agnostic to the source or the color of hydrogen, but there is a purity requirement on the hydrogen. That's the only requirement. The percent boil off. So how's the boil off managed with the Fortescue mining truck? Yeah. So the mining truck system has that first deployment had fairly rudimentary mechanisms for managing those systems as a sort of a first prototype deployment. There's massive learnings that have come out of that project and exactly how you are best to do those sort of refueling protocols and how you can manage the boil off systems. The tanks on the haul truck are actually triple skin tanks. So they're metal tanks, but they have that liquid vessel containment. So they naturally have a buffer that improves the heat leak or reduces the heat leak into the tank and manages the boil off. But yeah, I mean that site, there's still a lot of data coming out of it in terms of the efficiencies of those systems. The biggest thing coming out of it, though, is the learnings that would roll into the next deployment of a system like that.
Lovely. And the Samantha had a follow-up question on the triple skin composite. Are the layers all polymer based? I believe I also missed that one too. And for the GH2 in the chart at 350 bar, was that a type 3 or a type 4 storage tank?
Yeah. Okay, so the composite tank, the triple skin, they're 100% composite. They're actually a fiberglass composite. So all of the skins for the double skin or the triple skin tank, 100% composite. The GH2 on that chart is, I believe, actually it's modelled on another project that we're involved in, and I believe there's a Type 4 tank. The points, if you could call them that, on that chart are big blobs, right? Because it's indicative, because what do those fuel systems look like? It's not just the fuel that we're talking about, it's how it's contained in the fuel packaging. So depending on the details of your system, those spots will move around. But it's to convey the basic point. There's a huge difference in the gravimetric index of hydrogen stored as a high pressure gas compared to stored as a liquid, and how that stacks up against fossil fuels.
Wonderful. Okay, great.
This is Nico with GTI Energy. I was curious what the technical lifetime, assumed standard technical lifetime is for these tanks, or what you're aiming for, because there's a known, say, technical lifetime for steel tanks, the one that you're basically competing with, even though you have a significant number of advantages. I'd be interested to hear what you're aiming for, what the assumed lifetime will be for those tanks. So that's good for comparison reasons, and also for promoting the technology, so to say, when we have conversations internally or with partners for projects that involve liquid hydrogen. Thank you.
Yeah, no problem, Nico. Great question. It's early to say. Ultimately, what we're aiming for, ideally, we'd love thousands of cycles on these tanks, right? But is that actually realistic, and is that achievable? We've got experience going back for 2 decades. We've been making composite cryostats with these manufacturing techniques. That gives us the best body of information on a large number of temperature cycles of these vessels. So we have some confidence in large numbers of temperature cycles. I showed figures, composites are pretty well understood in terms of pressure cycles, the number of cycles they can undertake. Combining those together, though, is the amount of information that's currently available. There's more work that needs to be done to give us some confidence on where we can land. And there is a lot of work going in that space by FABRUM and others currently that will help inform that. The other piece of it is what actually is needed, and what sort of replacement rate would actually work for these tanks. What is the manufacturing cost, and how can that stack up economically? So a lot of interesting questions in there, and early days, but hopefully over the coming months and the next couple of years, that we'll have a much better picture on that.
Okay, thank you.
Great. And Ross, if you'd like to ask your questions.
Thank you. Also, thanks for organizing. I've been meaning to join all these meetings, and I reached out to Danielle, and I'm really grateful for the organization. Thank you. You guys are doing great work. I come from the gas turbine and oil and gas industry. That's why I put in my question about the comparison with diesel fuel impurities, to try to focus and recognize that, instead of maybe leading ourselves to believe we're working with pure hydrogen, which is mythological almost. And so acknowledging that the impurities are part of the process, and that they do poison, like I mentioned in the life expectancy of fuel cells. And there's different types of power systems, but that's just one example. And one case of how they can poison, they call it, the fuel cells with carbon monoxide, which can be even a fraction of a part per million potentially, but it's going to be there, and it's just going to affect the lifespan. So that's why I'm asking those kind of questions based on the sources. Are there other types of impurities? That's just one example I thought off the top of my head that are typical to watch out for. And then is that what leads to the polymer design, or are they designing for those kind of impurities, or will the polymer deteriorate and add impurities to the fuel system? So it's like a 2-part question: the fuel, and then the system over time introducing impurities. Thank you.
Yeah, thanks, Ross. And you're getting a little bit out of my area of expertise, but let me add some comments, my thoughts about that. Absolutely, there's impurities in everything at some level. There's all sorts of impurities. When it comes to hydrogen, the color of hydrogen has a big effect on the impurities. Of course, if you're producing hydrogen from an electrolyzer, you're not going to have the same issue with impurities that grey hydrogen I have where it's coming from oil and gas, right? So that's one factor. Also, if you're using liquefied hydrogen, that's a very nice way of cleaning up your hydrogen if you're depending on the systems that you have. But hydrogen, as you know, boils at 20 degrees Kelvin, so there's not a lot else that's gaseous or liquid at those temperatures, right? So impurities tend to freeze out during the during the liquefaction process. Incidentally,
Right.
that's the requirement on the purity of hydrogen feeding in the liquefier is not to do with any chemical process of those impurities. It's just the problem. It doesn't matter what it is; it will freeze out in the system. If there's enough of it in there, it'll block the system. You get a block of ice of your impurity and your problem. So you need to clean up your hydrogen to ensure that you don't block up the systems.
Good point. Thank you.
But yeah, the point about fuel cells is a good one. The challenge there is that it's a cumulative effect, right? So even if you've got tiny amounts of impurity, which you will always have, your fuel cell is always degrading, right? One molecule at a time, but it's happening. So that's a challenge with fuel cells, and that's one of the attraction, I think, to some of the other systems like developing combustion engines for hydrogen, because obviously a lot less concerned about impurities in the fuel. So so look, that's probably the most I can get into that question.
Thank you.
And Stephen Ross, if you'd
Yeah,
like to ask your question.
Can you hear me?
Mhm.
Yeah, thanks, Barry. I think this has been a great presentation. I was just curious about your liquefaction technology. You mentioned you use a refrigeration cycle. I wonder, is that a turbo Brayton cycle? What's the cycle to use? And do you have any experience with some of the cycles such as magnetocaloric or thermoacoustic cycles?
Yeah. So the cycle of our system is a pulse tube. It's a pulse tube cryocooler. It's a proprietary cryocooler design that is actually conceived of by a state-owned research institute in New Zealand, and FABRUM purchased the patent and developed the technology over about the last decade into a fairly robust industrial cryocooler that's now being deployed in these systems. So that cryocooler has nice advantages with regards to most cryocoolers work, apart from you're talking about the refrigeration type systems, but most cryocoolers work by compression and expansion of gas. That's often done using pistons to compress and expand the gas, and if you've got mechanical pistons, you have a real problem with lubricants at these cold temperatures, right? Lubricants freeze, you get a lot of wear and tear. So what's unique about the cryocooler in these systems is the piston is actually a pseudo piston. It's a plug of compressed helium. So there's a pressure wave generator in there that generates a pulse of compressed helium. That's a refrigerant gas. That's what's doing the compression and expansion. So there's no mechanical moving parts in the cold part of the system. So in terms of its reliability and maintenance requirements, it performs very well. So that's the system that underpins ours. We don't do turbo Brayton systems. Generally start operating at larger scales, maybe when you're getting to really, some do smaller systems, but you're talking about 5 ton a day hydrogen liquefier is probably about the smallest. You start using turbo expander technologies. We're operating less than half a ton a day scale, so we're very small scale hydrogen liquefiers. We're not doing anything ourselves with the refrigeration cryocooler techniques, but certainly aware and working with some other parties that are looking at developing those techniques, and they're very interesting, but still some way away, I think, from being a commercial option, to my knowledge.
Okay, thank you.
And Sumant, you had a question or a clarifying question for Barry?
Yep, very nice presentation. Appreciate it. Hope one of these days I get down to New Zealand to see the facility. Did you mention all of your experience with FABRUM is actually fiberglass as the material? Are you using carbon fiber? And is fiberglass, and just a follow-up question, is fiberglass pretty much governed by the same carbon fiber regulations every 5 years, recertification, 15 years or so? I'm just trying to learn this from you.
Yeah. So look, so the tank, we work with fiberglass and carbon fiber. The cryogenic shells in these tanks are fiberglass, because from our experience, it performs a lot better for these applications, right? You may know carbon fiber has challenges with microcracking when it's supplied for these sort of applications. So that's being developed, but we've got a lot of experience with fiberglass. It performs very well. So the cryogenic shells are fiberglass. We we can use and do use carbon fibre in other places due to the strength and lightweight. So, for example, the vacuum jacket, which is always at ambient temperature, there's no reason that couldn't be carbon fibre and take advantages of the carbon fibre. In terms of the regulations around the certification there, in the space that we're operating, that's still very much a moving feast and still to be established, right? There's still quite a pathway. These tanks will be flying on aircraft within the next 12 months, but the pathway to, for example, FAA or CASA certification is, still significantly longer than that. So, and that will answer a lot of those questions as we work through that process.
Thank you. Appreciate it.
And does anyone else have any last questions for Barry? Perfect. Sion?
Okay,
Take it
if
away.
there's no question, okay,
Oh,
thank you again. Okay, is there?
No.
No? Okay. Thank you again to everyone for joining today's HySky Monthly webinar. And thank you once again, Dr. Barry Prince, for sharing your time and expertise with our community. Don't forget to register for Flying High. I'll drop it in the chat. So have a great rest of your day, everyone. Thank you so much.
Thank you.
Bye, Barry. Thank you so much.
Thank you so much, Barry.
Thanks, Sol.
Bye, everyone.
Bye, Barry.